Welcome to an exploration of one of the most fascinating mysteries in physics, the evaporation paradox. Imagine a water droplet evaporating. It gets smaller and smaller, but something strange happens near the end. Let's start by understanding what classical physics predicts about evaporation. Classical physics tells us that as a droplet gets smaller, it should evaporate faster and faster. The evaporation rate is proportional to the surface area, where m is mass, T is time, K is the evaporation constant, and A is surface area. For a sphere, the surface area equals 4 pi r squared. This means the rate of radius change should be inversely proportional to radius. So smaller radius means faster shrinking, which predicts acceleration of evaporation. This graph shows the expected exponential decay, with the droplet shrinking faster as it gets smaller. But experiments show something completely different happens in reality. In reality, when droplets reach nanometer scales, evaporation slows down dramatically or even stops. This is the observed behavior. Evaporation proceeds normally but then mysteriously plateaus when the droplet becomes very small. So we must ask, why does this contradiction exist? What is nature hiding from us at these tiny scales? The first clue comes from something called the Kelvin effect. The vapor pressure over a curved surface is actually different from that over a flat surface. The Kelvin equation shows that vapor pressure PR over a droplet of radius r equals the flat surface pressure times an exponential factor involving surface tension gamma, molar volume 5m, radius r, gas constant r, and temperature T. For water, surface tension gamma is approximately 0.072 newtons per meter. This equation tells us that smaller droplets actually have higher vapor pressure, which should make them evaporate faster. The small droplet has more arrows representing higher vapor pressure, yet the paradox remains. But wait, this makes the paradox even more puzzling. If small droplets have higher vapor pressure, why do they stop evaporating? Let's calculate actual numbers to see how strong this effect is. Consider a nanodroplet with radius 10 nanometers, or 10 to the negative 8 meters. Plugging in the values, 2 times surface tension times molar volume divided by radius times gas constant times temperature. This gives us approximately 0.104. So the pressure ratio is e to the 0.104, approximately 1.11. This means at 10 nanometers, the vapor pressure is about 11% higher than over a flat surface. As the droplet gets even smaller, this effect grows exponentially. Now we encounter a crucial nanoscale phenomenon: disjoining pressure. When droplets become extremely small, molecular forces between molecules create an additional internal pressure called disjoining pressure. The disjoining pressure pi d equals the Hamaker constant AH divided by 6 pi times the film thickness h cubed. For water, the Hamaker constant is approximately 10 to the negative 20 joules. This pressure acts to hold the droplet together, opposing evaporation. These inward arrows represent disjoining pressure, squeezing the droplet from all directions. We must also consider the classical Laplace pressure in curved interfaces. The Laplace pressure equals 2 times surface tension divided by radius. Let's calculate this for our 10 nanometer droplet. Delta P equals 2 times 0.072 divided by 10 to the negative 8, giving 14.4 megapascals. That's 144 times atmospheric pressure, an enormous internal pressure. Approximately 140 atmospheres. This diagram shows the scale of pressure, from 1 atmosphere up to the extreme 140 atmospheres inside our nanodroplet. Now, we reach the heart of the paradox: nanoscale phase transitions. At nanometer scales, water molecules don't behave like bulk water anymore. Surface molecules have fewer neighbors, creating a different local structure. In bulk water, each molecule has approximately 4 neighbors and a tetrahedral arrangement. Surface molecules, shown in yellow, have only 2 to 3 neighbors, creating a different phase. Here's a key question. What happens to the energy required for evaporation in this situation? Let's examine the energy barrier for evaporation at nanoscales. The total evaporation energy equals the heat of vaporization plus additional surface energy contributions. The heat of vaporization for water is 40.7 kilojoules per mole. However, at nanoscales, the surface energy term becomes dominant. Surface energy per molecule scales inversely with radius. This graph shows evaporation energy versus radius. As radius decreases, energy required skyrockets, creating a barrier. To understand this better, let's use an analogy with glass transitions. Nanodroplets can enter a glass-like state where molecular motion becomes restricted. Think of how honey flows at room temperature, but becomes almost solid when cooled, even without freezing. Left shows liquid-like flow with disordered lines. Right shows glass-like structure with ordered but immobile molecules. The glass transition temperature increases inversely with radius for nanodroplets. This means smaller droplets can enter this glass-like state at higher temperatures than we'd expect. Another crucial factor is the formation of confined water layers. When only a few molecular layers remain, water exhibits completely different properties. Below 3 nanometers thickness, water enters the confined regime. Here we see 3 layers of water molecules confined between surfaces, showing the structured arrangement. The hydrogen bonding network becomes highly structured and resistant to disruption. The diffusion coefficient drops by orders of magnitude, making evaporation extremely slow. Now let's put all these factors together to understand the complete picture. Multiple competing effects create the paradox. Kelvin effect increases vapor pressure. Laplace pressure increases internal pressure, and disjoining pressure resists evaporation. The evaporation rate depends on radius, vapor pressure, Laplace pressure, disjoining pressure, and glass transition effects. Crucially, all these effects scale differently with radius, creating complex behavior. At a critical radius, typically a few nanometers, these effects combine to effectively stop evaporation. Let's estimate the critical radius where evaporation stops. We balance the Kelvin effect that promotes evaporation against disjoining pressure that opposes it. At the critical radius RC, Laplace pressure approximately equals disjoining pressure. This gives critical radius proportional to the cube root of Haymaker constant over surface tension. Plugging in numbers, cube root of 10 to the negative 20 over 12 pi times 0.072, giving approximately 2 nanometers. The critical radius is typically between 2 and 5 nanometers, depending on exact conditions. This tiny circle represents our critical droplet, just 2 to 5 nanometers across, containing only hundreds of molecules. What does experimental evidence tell us about this paradox? Atomic force microscopy experiments have directly observed these residual nanodroplets that refuse to evaporate. These tiny droplets can persist for hours or even days at sizes below 5 nanometers. This represents an AFM scan showing multiple persistent nanodroplets on a surface. The critical size depends strongly on environmental humidity and temperature. Critical radius is inversely proportional to the natural log of relative humidity. Temperature plays a fascinating role in this phenomenon. Evaporation rate follows Arrhenius behavior. Rate equals pre-exponential factor times exponential of negative activation energy over Boltzmann constant times temperature. However, the activation energy itself increases dramatically as the droplet shrinks. Activation energy equals bulk activation energy plus a term inversely proportional to radius. This graph shows evaporation rate versus temperature. The nanodroplet curve shows much stronger temperature dependence. Nanodroplets are exponentially more sensitive to temperature than bulk water. This paradox has important implications for many real-world phenomena. It affects cloud formation, as tiny water droplets in clouds exhibit this behavior. In inkjet printing and spray coating, the final drying stage is controlled by this effect. Medical aerosols for drug delivery must account for this to ensure complete evaporation or controlled residue. These scattered droplets represent an aerosol, where each droplet undergoes this evaporation process. Microfluidics and lab-on-chip devices operate at these scales where the paradox dominates. Let's address some key questions about this phenomenon. Can we prevent the evaporation slowdown? Let's think about this. Yes, we can prevent it by changing environmental conditions like humidity, temperature, or adding surfactants. How many molecules remain in a droplet at the critical radius? Number of molecules equals 4 pi rc cubed divided by 3 times molecular volume. For a 3 nanometer droplet, this gives approximately 4,000 molecules. Typically between 1,000 and 10,000 molecules remain in the final stable droplet. Impurities play a crucial and often overlooked role in this paradox. As the droplet evaporates, even trace impurities become concentrated and eventually accumulate at the surface. Final concentration equals initial concentration times the ratio of initial to final radius cubed. If the initial impurity concentration is just 0.1%, when radius shrinks from 1,000 to 3 nanometers, concentration increases 37 million-fold to essentially pure impurity. The final nanodroplet essentially becomes a concentrated impurity droplet. Left shows few impurities in large droplet. Right shows concentrated impurities in final nanodroplet. At nanoscales, non-equilibrium thermodynamics becomes essential. The classical thermodynamic approach is insufficient to explain the observed behavior at nanoscales. Instead, fluctuations and non-equilibrium processes dominate the behavior of nanodroplets. These inward arrows represent non-equilibrium effects, driving the system towards a new steady state. In conclusion, the evaporation paradox is a complex phenomenon. It arises from a combination of Kelvin, Laplace, and disjoining pressure effects. The critical radius depends on environmental conditions such as humidity and temperature. Nanodroplets can persist for hours or even days at sizes below 5 nanometers. This represents the persistent nanodroplets that refuse to evaporate completely.